Hi, and welcome to a video where I'd like to go through a worked out example problem to illustrate the vapor compression refrigeration cycle, and we will use a residential whole house air conditioning unit as an example. Today is my dad's birthday, so join me in wishing my dad a happy birthday. He passed away in 2001. Today, in 2023, he would be 105 years old. So I still think about my dad every single day. One thing that I remember in particular about my dad is when I was in high school and getting ready to go to Virginia Tech, the topic of conversation was air conditioning. An air conditioner. We had air conditioning units like this, a couple of these in our house, the window mount air conditioning units. And I asked about how does that work? And my dad's, he was a mechanical engineer from Virginia Tech. And he told me the components and how it worked. I was totally confused. I really didn't understand it whatsoever. And I'll have to tell you that he was very gracious about explaining it to me several times. I don't think I absorbed it. And it took me a long, long time to really understand how an air conditioning refrigeration cycle worked. So happy birthday to my dad. And so this worked out example problem would be dedicated to the memory of my dad. We're going to cover real quickly refrigeration cycle crash course. Perhaps I will try to recite the way my dad explained it to me, and hopefully you'll do a better job of absorbing it than I did. Then we're going to do a worked out example problem illustrating how to analyze a residential whole house air conditioning system. So here's the crash course first. What do all these, let's see, we've got 4 images. They all have something in common. What do they have in common? The refrigerator in your kitchen, a window mount air conditioning unit. Outside your home or apartment or townhouse, this thing that whirs around, it's a compressor and condenser for a residential heat pump or air conditioning system. Or the automotive air conditioner in your car. What do these all have in common? Well, they all operate in a basic refrigeration cycle, and it's my hope that this basic schematic comes to your head. Okay, remember this closed system operating in a cycle. The counterclockwise arrow indicates that it's kind of working backwards. Power is going into the system operating in a cycle. Power is going in, a little different. We're transferring heat from a low temperature reservoir up to a high temperature reservoir. So for your refrigerator and your air conditioner, this is what you're interested in, removing heat from a cold or cool space. If you're operating a heat pump in the wintertime, here's what your objective is. You're interested in moving heat up into a warmer space from a colder space. So that's what all 4 of those systems have in common. All 4 of those systems use the basic vapor compression refrigeration cycle to operate. So let's look at the components. I want to go through the components one by one, and I'm going to try to illustrate what those components look like. Let's start at the compressor, where the refrigerant comes into the compressor, power is coming into the compressor, and it's compressing the refrigerant up to a higher pressure and temperature, and then goes into a condenser, steady state, steady flow, a condenser where heat is rejected to a higher temperature reservoir until we get to a liquid refrigerant. Then that high pressure liquid refrigerant goes through an expansion valve. And it turns out that refrigerant gets very cold when it goes through this pressure valve, expansion valve. Pressure drops dramatically. Then we go into the evaporator, and that's where the action is for a air conditioner or refrigerator, where we absorb heat from the cold space. So 4 basic components of the vapor compression refrigeration cycle that you should have in your head: a compressor, a condenser, an expansion valve, and an evaporator. You should have those. You need to commit that to your memory. Let's go through them. Physically, what do these components look like? What does a compressor look like? Well, sort of this black vessel is what the compressor looks like. And here's a better cutaway view of a refrigerant compressor. Down below is the electric motor drive. You can kind of see the windings of the motor, and up higher is going to be the compressor part where the refrigerant goes in. It's compressed to a higher pressure and temperature, and then out it goes to the condenser. So that's what a compressor looks like. And a little bit more about that later on. What does the condenser look like? Now, if you go outside your home or your townhouse or your apartment, you're probably going to be able to find something like this if you have a whole house air conditioning unit or heat pump. Okay. So this is what you see out on the ground. Here's a cutaway view, and this unit contains the compressor in the middle of the unit. Let's not worry about that right now. The condenser is what basically you see through the louvers of this unit. It's a bunch of thinned tubes called condenser coils, and that's where the hot, high pressure refrigerant is condensed by rejecting heat to the surroundings. And the way that the surroundings pass across that coil is this fan that pulls the outside air across those coils, pulls it up through the fan, and then warm air is discharged back up to the surroundings, up in the upwards direction. That's what the condenser looks like. The expansion valve, it's something you could hold in your hand. You can go to Lowe's or Home Depot and buy an expansion valve. Okay, here's what it looks like. Here's a photograph. Here's a schematic of it. This high pressure, high temperature refrigerant is coming in. It goes through, there's a little control valve actuator, and this flow goes through a tiny little orifice, a tiny little hole. That's the pressure drops because of the resistance to flow. And so then the flow comes down, the pressure is dropped, the refrigerant gets very cold, and then out the refrigerant goes to the evaporator, expansion valve. Finally, evaporator. This is an example of an evaporator of a whole house air conditioning unit. Well, the evaporator is the refrigerant is going to go in, the cold refrigerant goes in this copper tube. It winds its way through this thinned tubing, okay? So very cold refrigerant. Warm air from your house blows through across these evaporator coils, cooling down that air, and then you get nice cool supply air, keeping you cool, going back to your room. This is the evaporator. So this is a schematic. There's a blower either down in your basement or in a utility closet, blowing air across the evaporator, and then nice cool supply air coming back to you in ductwork. Okay, so I hope I've given you a crash course in the 4 major components of an air conditioning system that works on the vapor compression refrigeration cycle. Let's see, compressor, condenser, evaporator. Darn it. Let's start again. Compressor, condenser, expansion valve, evaporator. Those are the 4 major components. Okay, so here's going to be our example problem where we're going to determine the power needed to run a whole house air conditioner, as well as determining the coefficient of performance for the air conditioning system. And here's our problem. A residential air conditioning system is rated at 1.5 tons. This is the way you go and purchase an air conditioner from Home Depot or Lowe's or an HVAC commercial installer. 1.5 tons of cooling. It uses refrigerant 134A. The condenser discharge pressure is 800 kPa. The isentropic compressor efficiency is 80%. The compressor inlet condition is saturated vapor going into the compressor, saturated vapor. The condenser outlet condition is a saturated liquid. Very common. These are just very common situations in the real world. The evaporator pressure is 240 kPa. Changes in kinetic energy of the refrigerant throughout the cycle are negligible. Okay, and so here's our assignment. Determine the evaporator temperature, the maximum temperature of the refrigerant. That's going to be at the discharge of the compressor. The mass flow rate of the refrigerant needed to deliver 1.5 tons of cooling to the house. Okay. The power required to run the air conditioner. Pretty reasonable engineering question. And then finally, what's the coefficient of performance of this air conditioning unit? You're going to need to be able to do this. Oh, test prep. Now, this probably would be a pretty involved single problem for a test. However, imagine the number of questions if you split out specific analyses that goes into this. You can almost count on this being a test or exam problem. Some part of this will be a test or exam problem. All right, let's start with a sketch. Well, let's sketch the air conditioner system. You saw this before, but you should be able to do this by hand, pencil and paper. I'd say this is a pretty professional drawing. I made a screen clip out of the book, but it involves and clearly labeled state 1 going into the compressor, state 2 leaving the compressor. Let's see, it said going in is saturated vapor. State 2 leaving the compressor going into the condenser. State 3 leaving the condenser. It's going to be a saturated liquid. The condenser is where we reject heat to the surroundings. Very hot condenser refrigerant, very hot. Okay. 3 to 4 is the expansion valve process where the pressure drops and the refrigerant gets very, very cold. The evaporator. Now, here's you. We've got a residential air conditioning unit. Here's you staying nice and cool. So the objective is 1.5 tons of cooling, the cooling effect, 1.5 tons. We'll get the unit straight on that later. Keeping you cool. Q.L or Q.N in the textbook is 1.5 tons of cooling effect, keeping you cool. And then back to the inlet of the compressor as saturated vapor. Okay, there's your sketch equipment diagram. Okay, the next thing to do before we start doing any numerical work is draw a TS diagram. This blue vapor dome is a to-scale drawing of a TS vapor dome for refrigerant 134A. Looks a little different in shape than a vapor dome for H2O, but this is the to-scale drawing. So let's look at the system. The cycle. I've tried to show my counterclockwise arrow. We're going in a counterclockwise direction. That means power is going to be needed to run the cycle. All right. We're coming into the compressor as saturated vapor. We're on the dome. We're going to study the isentropic compressor process, 1 to 2I, but we're going to recognize our compressor is adiabatic but irreversible. So we're going to be going on a dashed line, an irreversible process to state 2A. Your book's going to call this state 2. I like to call it 2A. And our pressure, our condenser pressure is 800 kPa. We're coming into the compressor at 240 kPa. Come out of the compressor at a high pressure into the condenser. We're going to condense that vapor. We're going to condense the refrigerant vapor down to a saturated liquid at state 3. We're going to go through the expansion valve, very irreversible. No power is produced from the expansion valve. Think about the image I showed you. Very irreversible process, 3 to 4, where we're going to come in to the evaporator. Saturated mixture, a cold saturated mixture at state 4 and then we're going to absorb heat from the room to keep you nice and cool and go back to state 1. So that's our TS diagram. Now, you might want to study this TS diagram by downloading the static slides attached to this video. All right, so let's look at the solution approach. So I've listed, here's what we're looking for. Wow, the evaporator temperature. That should be easy. We know P1 equals P4. All we got to do is go to our pressure table for R134A and look up the saturation temperature, the boiling point. That's the evaporator temperature. The maximum refrigerant temperature. It says we need 2A, need H2A. Let's go back a couple of slides. The maximum refrigerant temperature. Okay, that's the beauty of drawing this TS diagram. Where's the maximum temperature? I'm going to look them up. There it is. There's the maximum temperature of the refrigerant, state 2A. So I'll need H2A, okay? Well, in order to get H2A, I'm going to need W actual kilojoules per kilogram, the actual work needed to drive the compressor. And then we'll use the first law to get H2A. We know P2, that gives us two independent properties. And so we'll back solve, we'll interpolate for T2 actual. The mass flow rate. Well, let's see, what do we need QL. We need to do our cycle analysis to get QL in kilojoules per kilogram. On a kilogram basis, how much heat is removed from the cold space? Well, Q dot L is given. The rate of heat removal, the cooling effect is given 1.5 tons. So we're going to need to do some unit conversions to get tons of cooling into kilowatts. And that way we'll get our unit straight and we're going to be able to back solve for M dot. It's going to be Q dot L over little QL. Once we got the mass flow rate, it's easy to calculate the power required. W dot, the rate of work done, the power needed to run the compressor is simply going to be M dot times W actual of the compressor in kilojoules per kilogram. Finally, coefficient of performance, energy sought over the energy that costs. We'll figure that out. We don't need a formula sheet. The energy sought, well, that's QL. That's the cooling effect in kilojoules per kilogram divided by the energy that costs us to run the air conditioner or refrigerator is W actual of the compressor. For this cycle, that's the only place that work occurs is driving the compressor. The expansion valve has nothing to do with work. Okay, so now we can start looking at numerics. Okay, let's go to our pressure table for R134A. We'll find our pressure, P1 equals P4. There it is, 2.4 bar, 240 kPa. And so immediately we've got at least one answer for our analysis. Our evaporator temperature is minus 5.37 degrees C. That's cold. Whew, that's going to be cold. That's going to keep us nice and cool. All right, so there's one answer. We're going to write down the properties we need both at states 1 and pressure 2. So let's look at H3 first. We remember on our TS diagram, we recall that the exit of the condenser, that's state 3, is saturated liquid. So we'll go to P2, the high pressure, and look up H sub F and write it down, 93.42 kilojoules per kilogram. Okay. At state 1, we're going to write down both H1. We know we'll need that for the first law. And we'll also write down S1. Okay, let's see, 244.09 on H1, 0.9222 kilojoules per kilogram degree K for S1. And we know we need S1 because we're going to do the isentropic analysis for the compressor. So we'll write down S1. And then let's see, at P, we're going to need to, we're going to get a little extra credit. And so we're going to write down H sub G and H sub F at P2 in order to solve for the quality at state 4. So we're just going to write down HF and HG. So Wow, look, I already wrote down 244.09. That's Hg. So that's the inlet enthalpy going into the compressor. That's Hg. Okay, so now we're going to do the isentropic work. We're going to study the isentropic work for the compressor. Well, let's see. We need H2 isentropic to do that first law analysis. So let's see. We looked up S1 for the isentropic compressor. S2 isentropic equals S1, 0.9222. We're going to go to our superheated tables at 8 bar, 800 kPa, and we're going to shop for where can we need S is 0.922. I don't see it, but it's in between these two numbers. So it's somewhere between saturation temperature, 31.33 degrees C, and it's somewhere between 31.33 and 40. So we will do the interpolation. We've got to do the interpolation on H. So do you see how that translates there? And we'll discover that H2 isentropic is 268.97, linear interpolation. H1 we already wrote down. We'll apply the first law for the adiabatic compressor. For the compressor, Qn is 0. Compressor, adiabatic compressor, Q is 0. So let's see. Q minus W isentropic is equal to H2I minus H1. I didn't go through all those steps, but do you see that you can solve? So you see how this is a statement of the first law for the compressor. And so for the isentropic process, so W isentropic is negative 24.88 kilojoules per kilogram. Makes sense, makes sense. It takes power to run the compressor, so I'd better get a negative number for W isentropic, negative 24.88. Okay, that was studying the isentropic compressor process. Now we're going to go back, look at our TS diagram, and study the actual compressor process. And we're going to think about compressor efficiency. We should be able to figure this out in our heads without going to a formula sheet. Let's see. For an adiabatic compressor, which would you think would take less power to run? A compressor that's reversible and adiabatic, or one that has irreversibilities? I think the reversible one. So the compressor efficiency must be W reversible over W actual. So therefore, W actual is the reversible work, kilojoules per kilogram, it's W dot over M dot, divided by the compressor efficiency. So we'll do the math, all right? Negative 24.88, we just found that. Divide by 0.8 to get the actual work, W dot over M dot, needed to drive the compressor is negative 31.1 kilojoules per kilogram. We're going to need that for the coefficient of performance. But we're also going to use that to determine H2 actual. All right, so there we go. Now we're going to work on the maximum refrigerant temperature before we move along. We're going to apply that first law for the actual adiabatic compressor process. Qn minus W out actual equals H2A minus H1. We do our little algebra to get H2 actual equals H1 minus W actual. So H2 actual is going to be a bigger number than H1. W actual was negative. Okay, so we're going to get, let's see, here we go. I just wrote that down from the previous slide. H2 actual is 275.19. That gives me my second independent property at 800 kPa. Go back to our superheated table, 800 kPa. I've got to shop around for H2A is 275. 275. Oh, here it is. In between these two numbers. In between these two numbers. So our T2 actual is somewhere between 40 and 50. All right. If you're taking a test and you're running out of time, at least write down T2 actual, the maximum temperature is going to be somewhere between 40 and 50, and you'll get partial credit. But let's do the interpolation. All right, so here's our H2 actual. Here's the two H values from the superheated table. Here's the two temperatures. So our temperature is in between those two. We'll do a linear interpolation to get the answer the question. Our maximum refrigerant temperature is 41.42 degrees C. That's hot. That's hot. 41 degrees C is hot. Now we're going to move on to the expansion valve, because the way this problem was worded, we don't even have to analyze the condenser. We're going to move right to the expansion valve. Remember that let's write the first law for the expansion valve. Here's a picture of it. It's fully insulated. The expansion valve is considered to be fully insulated. No heat loss to the surroundings. Okay. Do you see a shaft rotating? Is this valve lifting a weight? No. So, and we'll divide by m dot to get little q in, adiabatic, minus little w out, there's no rotating shaft, equals H4 leaving minus H3 entering. Okay. So, well, statement of the first law for the expansion valve, no change in kinetic energy, H4 equals H3. Easy. So there's H3. So there's H4. Now, I got, just to get a little extra credit, it is not necessary to determine the quality at state 4 to solve the questions asked. But I want to show you, how would you determine the quality at state 4? Well, I wrote down Hg and Hf at the evaporator pressure. I know what H4 is, so I can use the definition of quality I know in my head, or at last resort, you could look at your formula sheet to see that definition of quality is the quantity H4 minus HF divided by the quantity Hg minus HF. Really very easy calculator work. And so the quality at state 4 is 25%. 25% quality going into the evaporator. Okay, now we're going to determine the evaporator heat transfer, Q dot over M dot. Okay, so let's see. First law for the evaporator, Q in, that's what we're looking for, minus W out. Is the evaporator lifting a weight? Is there a shaft turning, producing power or requiring power? No. So there's no rotating shaft. Q out is 0. And so H out minus H in, H1 minus H4, that's H leaving, H entering, here's Q in. So we'll solve straight out for QL. Q into the evaporator is plus, it's going in, 150.67 kilojoules per kilogram. We're going to need that. We're going to need that in order to determine the mass flow rate, M dot. So we remember this off the top of our heads. Q dot L equals M dot times little QL. We just found little QL. How do we find Q dot L? Well, that was given, okay? Given 1.5 tons of cooling. So there's a conversion factor in the back of your book. It says that 3,413 BTUs per hour equals 1 kilowatt. See how I did that? 3,413 BTUs per hour equals 1 kilowatt. Okay, so I wrote that down. Okay, I got off track. Pardon me. I need to look higher on my slide. 1 ton of refrigeration. I'm sorry. 1 ton of refrigeration is 200 BTUs per minute. If I multiply by 60 times 200, 12,000 BTUs per hour equals 1 ton of cooling. All right, so now I'm back on track. Q dot is 18,000 BTUs per hour. Now, okay, there's 3,413 BTUs per kilowatt hour. So Q dot is 5.27 kilowatts. Q dot is 5.27 kilowatts. So now I've got all my units straight. Look, what was little q? Little QL. Darn it, I didn't write it down on this slide, but I saw for Q dot divided by QL is 0.035 kilograms per second. So let's look at my units. So m dot, so I multiply by 60 to get m dot is 2.1 kilograms per minute. 2.1 kilograms per minute. Okay, so we found m dot. Next, we'll do the coefficient of performance because we've got everything we need for the coefficient of performance. Coefficient of performance is energy sought over the energy that costs, QL or W actual of the compressor. We got all of that work from work we've done. So our coefficient of performance is 4.85 for a residential, very reasonable coefficient of performance for the real world operating on the vapor compression refrigeration cycle. 4.85 is the COP. The power required to run the compressor, well, let's see. How could we get that? Well, we'll remember that W dot of the compressor is M dot of the refrigerant. We just found that times WA of the compressor. We've got that, okay? So plug and chug now. And so there we go. W dot of the compressor is negative 1.088 kilowatts, or in other words, 1,088 watts. Now let's see, is there anything you use from time to time that would be around 1,000 watts? A hair dryer, a hair blow dryer is about 1,000 to 1,500 watts. And so the equivalence there, so to run a 1.5 ton air conditioning unit is about the same as running a hair dryer, 1,088 watts. Okay, we're done with the worked out example problem. So let's recap with the results. The evaporator temperature we found, just using the pressure table, negative 5.37 degrees C. We found the maximum refrigerant temperature by analyzing the actual compressor, 41 degrees C. We found the refrigerant mass flow rate needed to give you that 1.5 tons of cooling effect, 2.1 kilograms per minute. We determined how much power it takes to run the compressor, 1,088 watts. And we determined the coefficient of performance of the refrigerator, 4.85. Energy sought over the energy that costs. So here's the recap of our engineering analysis. We started with the isentropic compressor. Then we determined the actual compressor outlet state using the first law, and we determined work actual. Then we jumped over to the expansion valve. And so we determined the ingoing enthalpy going into the evaporator. That was everything we needed to determine the evaporator cooling effect, little QL. And once we had little QL and the given amount of cooling effect, we were able to determine the mass flow rate. And so then finally, we were able to determine the coefficient of performance, beta, and the actual power required. So that's what we did in our analysis. And so one last thought before I leave you. Imagine a life without air conditioning. Also imagine a life without refrigeration. So I was very young in the early 1950s. Air conditioners became widely affordable at that time. It was a big family event. And my dad was an engineer, and we were able to afford as a family a window air conditioning unit. That was a big accomplishment for us as a family. Imagine living without air conditioning nowadays. The other fact is that in some countries, air conditioning is not affordable. And so we're very fortunate to live where we live and to be able to afford air conditioning in the places that we live and we work and we shop and that type of thing. Again, happy birthday to my dad today. Thank you for everything. And I hope that this video has helped your understanding of how the vapor compression refrigeration cycle works.